We are now going to consider the two main results on bases. The first one is the following. It is an equivalence between four statements, and they are all equivalent for a certain number of vectors to be a base of a vector space. So the following are equivalent. So S, a set S of finitely many vectors v1 through vn is a basis of V. V is a vector space. I'm not going to specify this. So this is equivalent to the following statement. For each vector V in the vector space big V, there exists a unique linear combination of the vectors vi representing V. So V equals sum for I goes from 1 to n of, let's say, alpha I vi. Okay, so here we can remark the following things. So the existence part is equivalent to the VI's being generators. Okay, generators means that every vector in the vector space is a linear combination of these vectors. So existence if and only if VI's are generators. VI are generators. And the uniqueness of the linear combination is equivalent to the linear independence of the VI's. VI are linearly independent. So since by definition a basis of a vector space is a set of linearly independent generators, then we see why B is equivalent to A. So statement C is the following. S is a minimal set of generators of V. So minimal is exactly in the same sense as what we explained before, which is so if we remove one of these n vectors from the set, the remaining ones will not be able to generate all V. And then the last statement is the following. D S is a maximal set of linearly independent vectors of V, i.e. for every V, for every, let's say, W in V, S united with W will be linearly dependent vectors. An immediate corollary of this result is the existence of bases for every vector space. I just remind you that we are assuming the vector spaces in this course are all finite dimensional, and here we will use it. Okay, so corollary: any vector space has a basis. How do we prove that? Okay, we take a finite set of vectors which are generators, and these exist by assumption, since any vector space is finite dimensional in this course. And then from these finitely many vectors, we start removing those that are linear combination of the others. And at some point this process will finish, because these vectors are finitely many. And the ones remaining will still generate all V, and the set will be minimal, in the sense that if I will remove any of the remaining vectors, I will not be generating V anymore. So by this result, we know that this is going to be a basis of the vector space. The result also implies that I can construct bases starting from, instead of starting from generators, starting from linearly independent vectors. So I start from a non-zero vector V1, let's say, and then I take in the complement of V1, or let's say I take a vector outside the vector space generated by V1, and I consider the set V1, V2. V2 is a vector outside the vector space generated by V1. These will start the process, and then the third step will be taking a vector V3 outside the vector space generated by V1 and V2, and so on. Eventually, when I will not be able to find vectors outside the vector space generated by V1 through Vn, it means that they are generators of all the vector space V, and they are all linearly independent. Therefore, I got a basis also starting from the bottom. I can start from the top, meaning generators, or I can start from and removing vectors from the set, or I can start from the bottom, keep adding linearly independent vectors. These are the two techniques to obtain a basis in a finite dimensional vector space. So this somehow indicates that, or suggests in a sense, that a set of generators for a vector space could have more vectors than any linearly independent any set of linearly independent vectors. And in fact, this is the case, and we will see this as a corollary, or at least on the way of proving the second main theorem. So number 2, this is called basis extension theorem. So we have two sets, one of linearly independent vectors in V and one of generators. So let I, so we introduce the notation for the vectors in I. There will be V1 through VH linearly independent vectors in a vector space V, and G W1 through WK be generators of V. Then there exists a subset of G, which we will call G prime. There exists G prime included in G, such that if we take the union of I with G prime, this will be a basis of V. Is a basis of V. From the proof of the basis extension theorem, we will see another very interesting theorem, namely that the number of elements of a set of linearly independent vectors will always be less or equal than the number of elements of generators of a vector space. So using the same notation as the one in the theorem, we will have that the number of elements of I will always be less or equal than the number of elements of G. Well, this will be a corollary of the first step of the proof of the basis extension theorem. So I state it as a fact here. And then this theorem will have an immediate corollary, which is fundamental. So all the bases, basis of a vector space V have the same number of elements. But this is because I can consider two bases independently as a set of linearly independent vectors and generators at the same time. So if I consider two bases B1 and B2, first B1 as linearly independent vectors and B2 as generators, and then B1 as generators and B2 as linearly independent vectors, we will see that at each step we will have inequality that goes in a different direction. Therefore, the equality must hold. This implies that the following definition is well posed. Definition: the dimension of a vector space V is the number of any of its bases. Okay, so this is well posed because of the corollary. I can pick any of the bases of V and just count the elements, and this number will be the dimension, and the number will not depend on the choice of the bases. The last result we will state in this lecture is still a corollary, and is as follows. So we suppose that the dimension, assume the dimension of a vector space V. So dimension of V is the short of the dimension of any vector space. So we will indicate dimension of V as dim V. Okay. So let's assume the dimension of V is n. And then we assume that we have n linearly independent vectors in V. Okay. So we can conclude that they are generators. Then n linearly independent vectors in V are generators. Vice versa, n generators are linearly independent How do we prove this corollary? So for the first statement, we will have to use the basis extension theorem, because if I have n linearly independent vectors, according to the extension theorem, I can complete them to a basis of V, adding some vectors from a set of generators. But if they are not already a basis, meaning if they're not already generators, then I will end up with the basis with the number of elements strictly greater than n, contradicting this corollary. The corollary that states that all the bases of a vector space have the same number of elements, and here we are supposing that the dimension of V is n. Therefore, the number of elements of a basis of V must be n. Okay, so if they are not generators, then I can complete them to a basis with the strictly greater than n number of elements. Vice versa, if I start from n generators, if they are not linearly independent, I can remove some of their vectors until I get a linearly independent set of vectors, which will be again generators, and that will be a basis of V with the number of elements strictly less than n, again contradicting the corollary that all the bases of a vector space have the same number of elements. In the next lecture, we will prove the basis extension theorem.